give our last sort of formal colloquium of the semester. So those of you who work on neutrino experiments know that there's a very important result that came out recently from the T2K experiment, and Jonathan, Dave, and myself thought it was very important that we have somebody who's an expert from T2K come and tell us about that result as a colloquium post-haste. So I decided to invite Alysia, who's at the University of Colorado Boulder. So Alysia has worked on various neutrino oscillation experiments. Her award-winning PhD thesis was on the SNOW experiment, which, as many of you know, shared the Nobel Prize for discovery of neutrino oscillations last year. And she's also worked on the MINOS experiment, as well as NA61 and SHINE. So after PhD at Berkeley, she went to do postdocs at Fermilab and University of Toronto, and then since then has been a faculty member at the University of Colorado Boulder, where she's now an associate professor. And we know each other because we worked together on the Dune high-pressure gas near detector. So I think that's enough of an introduction. And so thank you all for coming to this remote colloquium. And I'll hand it over to you, Alysia.
Okay, all right. Thanks very much for virtually inviting me. Today I'm going to be talking about discovering neutrino properties with long baseline beams, and I'll start off with an introduction reminding you about what are neutrinos and how we describe neutrino oscillations, and then I'm mostly going to focus on the T2K experiment, talking as an example of how we make a beam of neutrinos, how we detect neutrinos, and what we've learned, and again, especially the result that came out in the past month, and I'll say a little bit about what the future for long baseline neutrino beams holds. And so just a reminder, this is kind of like the periodic table for the standard model of fundamental particles. The particles are arranged here in columns that are sort of controlled by how the particles interact. So we have quarks on the left and we have leptons on the right. The neutrinos are here all the way over on the right. There are three types of neutrinos, each one electron neutrinos, muon neutrinos, and tau neutrinos. There's also a corresponding charged lepton that goes with it. The particles over here, the quarks, can interact through all of the fundamental forces. The neutrinos are almost kind of like, the noble gases or something. They're kind of the least reactive. They have no electric charge and very tiny masses, and so they only interact through the weak force, which means that they can travel through large amounts of material without interacting, and this gives them interesting properties and makes them a challenge to detect in the lab. All of these matter constituent particles also has a corresponding antiparticle as well, and so even though neutrinos are pretty difficult again to detect, they're actually very numerous and abundant in the universe. If you were to try to look at the neutrino sources in whatever room you're sitting in, the largest flux is actually coming from neutrinos left over from the Big Bang. As you move higher in energy and a little bit lower in flux are the neutrinos coming from the core of the sun, and there are about 100 billion of those passing through your thumbnail every second, day or night. We then have neutrinos coming from supernovae, and so these could be a really energetic burst, like from supernova 1987A, but there's also kind of a relic continuous background from all the supernovae scattered around the universe, and these are in particular core collapse supernovae, like type 2 supernovae, where actually neutrinos carry off about 99% of the energy in the supernova explosion. Moving a little higher in energy, we have atmospheric neutrinos. These are produced when cosmic rays strike the Earth's atmosphere, and we get neutrinos associated with that. They're also produced in a lot of common radioactive decays, and so, for example, like your typical banana emits like about 1 million neutrinos per day due to the tiny amount of naturally occurring radioactive potassium inside them. So we are also all probably giving off a couple million neutrinos per day. So they're very common, but they interact pretty rarely, and it's taken a long time to learn about them. But in the past 25 years, we have pretty compelling evidence for neutrino oscillations. And again, there are three different flavors of neutrinos, and there seems to be some evidence that they can change from one flavor to another. And the first strong piece of evidence came from atmospheric neutrinos. which again are muon neutrinos and electron neutrinos. Their flux should be symmetric around the horizon. And while Super Kamiokande saw that for the electron neutrinos, something seemed to be happening to the muon neutrinos. They seemed to be, the ones that were coming from below and traveling a long distance through the Earth, seemed to not be muon neutrinos when they arrived there anymore. Something was happening to them. And then we also have pretty compelling evidence that what's happening is that they're changing flavor coming from the solar neutrinos. So the sun only produces electron neutrinos in the fusion reactions in its core, and this is the summary of the fundamental overall reaction. And the Sudbury Neutrino Observatory used heavy water and was able to detect only electron neutrinos through one channel, and also had another channel that was sensitive to all active neutrino flavors. And what they saw was that the total flux of neutrinos that they could see coming out of the sun was in very good agreement with what had been predicted. And for decades, people kept looking for these neutrinos coming from the sun and seeing a lot fewer because they were primarily only detecting electron neutrinos. But when you detect all the neutrino flavors, you've got roughly the right number. But indeed, only about a third of them still seem to be electron neutrinos by the time they reached us here on the Earth. So there's strong evidence that neutrinos are somehow transforming as they travel through space from one kind into another. And the 2015 Nobel Prize was awarded to the spokespeople of Super Kamiokande and Snow for this discovery of oscillations. Since then, these results have all been confirmed with artificial neutrino sources, including accelerator-generated beams and also reactor antineutrinos. So how can we understand these neutrinos changing from one type of neutrino to another? We can understand this because it appears that neutrino flavors seem to not be quite the same as the neutrino mass states. So when neutrinos are produced, they have one of three flavors, each of which corresponds to a charged lepton. But these appear to not be the mass states or the energy eigenstates of the vacuum. There seems to be some mixing between them. And it's this interference between the flavor eigenstates and the mass eigenstates that will cause the neutrinos to appear to start with a particular flavor, but then potentially transform into another flavor as they travel through space and time. And this mixing between the different masses and how they make up the different flavor states are made up of these different mass states is controlled by a 3x3 unitary mixing matrix, the PMNS matrix. So I'll step back just and consider a slightly simpler case where if we imagine that we only had two neutrino flavors, then this mixing matrix just becomes a simple rotation matrix with just an angle theta 1, 2 in this case. And so this tells you, for example, for flavor alpha, how much of mass state 1 and mass state 2 you contribute to these two different neutrino flavors. So we can ask if we start with neutrinos or a neutrino with a well-defined flavor at t = 0, it's made up of some particular mixture of mass state 1 and mass state 2. And so if we propagate the state and let it evolve over time, if we assume the neutrinos have a well-defined momentum, then the two different neutrino mass states have slightly different energies. And if these states are evolving with slightly different energies, it means they have slightly different frequencies. And so if you start off at t = 0 with a particular mixture of mass 1 and mass 2, at some later time, you have a slightly different mixture of mass 1 and mass 2. And that means you can't be in exactly the same flavor that you started off with anymore. You've started to pick up other flavor components. And so you can try to ask what's the probability if you start off with flavor alpha, what's the probability at some later time that you observe flavor beta, and for this two flavor case you get a fairly simple equation like this. And it is sinusoidal in the distance that the neutrinos have traveled, or really in the distance divided by the energy. So if I start off in flavor alpha, at some later time, there's a non-zero probability that I could measure a beta flavored neutrino in my experiment at some later distance. This sinusoidal part also depends on the square, the difference in the square of the neutrino masses. So it's the mass of one state squared minus the mass of the other state squared. And then also there's mixing angle controls how much mixing we have. So in this particular case, I'm showing you what the probability looks like as a function of distance. And again, it's sinusoidal. More typically in an experiment, your distance is fixed and the energy, you have a spectrum of energy in your experiment. So if we were to plot the survival probability as a function of energy instead, you see something like this. And how deep this well goes, so how big your probability is of changing to another flavor, that depends on this mixing angle coming from that matrix, and exactly what energy, where this you get the maximum probability to change to another flavor. That again depends on this delta m squared. Again, delta m squared, it's the difference in the squares of the masses, and so this can be positive or negative, which will be important a little bit later. So this is the situation for 2 neutrino flavors. For 3 neutrino flavors, it's the same idea. It just gets a little bit more complicated. Our 2x2 mixing matrix is now a 3x3 matrix that looks very much like the product of 3 rotation matrices. So we now have 3 angles to parameterize this mixing. And then there's also this extra complex phase over here. And so all of these mixing angles are now known to be pretty sizable and to not be zero. There's a sort of similar mixing that occurs for quarks, but there the angles are very small. This matrix is very close to unity. For neutrinos, these angles are quite large. And again, one of them may be as large as 45 degrees, which would mean that you actually get maximum mixing between those two mass states. So this, again, typically, so we really do have to think about full 3 flavor matrix now, although a lot of times maybe only 2 parts of this matrix will dominate what you see in an experiment. For accelerator neutrino experiments, it tends to be dominated by this part of the matrix and not as much by what's going on for solar neutrinos. That doesn't really matter for long baseline beams until you get to a longer distance. So this is the matrix that describes neutrino mixing. Antineutrinos mix with the complex conjugate of this matrix. And so most of the matrix is real. It's just this e to the I delta term here. And so if delta is not equal to 0 or pi, then neutrinos and antineutrinos don't quite have the same matrix anymore. And that will also become important in this later. So I'll try to summarize what we know about neutrino masses and mixings, and this is based on a lot of different neutrino oscillation experiments with a lot of different types of detectors and neutrino sources, and also there have been a number of experiments that haven't seen neutrino oscillations as well. And so when you put this all together, we get a pretty convincing picture and have a pretty good idea of what are the parameters that can describe this oscillations. And again, there are these 3 mixing angles and also these mass splittings, and we don't get them from theory at the moment. They're things that people have had to go out and measure and again combine a lot of data to get this. From solar neutrino experiments and from atmospheric neutrino experiments, we already know that those are sort of occurring at different distance over energy scales. And so that tells us we know there must be at least 2 mass scales that are somewhat different from each other. They're a couple orders of magnitude apart. And if we look at electron neutrinos, if you look at long distance oscillations of these electron neutrinos, or really electron antineutrinos, from nuclear reactors, like from the Canland experiment, we know that there is pretty significant mixing. You see large amplitude disappearance. It doesn't quite go all the way to 0, so we know that this mixing angle, it's not quite equal. It's not quite 45 degrees, but there's still pretty significant mixing. When we look at muon neutrinos that are made in beams, we know that nu mu and nu tau seem to have almost complete mixing. The mixing angle here seems to be nearly 45 degrees. You have certain energies where a particular flavor seems to completely vanish. And so we know there's a large mixing angle, and that means that, again, we have roughly equal amounts of mu and tau making up these mass states. And we can also look at really short distance reactor antineutrinos, for example, And we know that on this shorter scale where this larger delta M squared becomes more important, we do know there is a little bit of oscillation here. The amplitude here is pretty small, less than 10%, but we do know that there is at least some nu E component here, but most of the nu E component is in these two lower masses. And so again, this has taken, a dozen or more experiments to sort of give us this picture of how much of the different neutrino flavor states make up the different mass states to figure out what these parameters are. There is one thing we still don't quite know about this mixing scheme, and we know again that there are two mass splittings, and from solar neutrinos, we know that nu2 is heavier than nu1, but this other state that we're calling nu3, we don't know if this is the lightest state, or if it's the heaviest state, which would be the normal ordering, or if it's the lightest state down here in the inverted ordering. So there are two possible ways that these states can be arranged, and it's something still we're trying to figure out with long baseline beams. Okay, so for three flavor mixing, again, the equations become a little bit more complicated than what we saw for two flavor, but roughly, if you have a beam of muon neutrinos, and muon neutrinos are the easiest to make with an accelerator beam, you can ask what's the survival probability. So the probability you still have a muon neutrino, and it's mostly controlled by this angle and this mass splitting. For electron neutrinos, the probability that a muon neutrino turns into an electron neutrino is controlled by this equation, which depends on two of the mixing angles. And so as we try to make more and more precise measurements, we need to use really this three flavor picture, and actually even need to include sometimes some higher order terms here as well. So this is what the equations look like in vacuum. When the neutrinos travel through matter, the situation gets a little bit more complicated, and that's just because matter has electrons in it. It doesn't have a lot of positrons or mu's or taus. And so any neutrino can scatter off an electron with a neutral current process like this that occurs equally for any neutrino flavor. But electron neutrinos have an extra process that's available to them through a charged current process through the exchange of a W boson. And so this modifies the potential a little bit. It doesn't mean that the electron neutrinos are sort of scattered away necessarily, but it modifies the potential and modifies the energy eigenstates a little bit. And so it changes the oscillation probabilities a little bit, but it's an effect that can be calculated, and it depends on the electron density of the material that you're going through, and it also depends on delta M squared, but in a way where the sign of delta M squared matters. When we're in vacuum, the sign of delta M squared doesn't matter, but when we're in matter, you start to pick up differences due to this part of the matter effect. And this is something that an effect that becomes more pronounced with more energy and distance. So this means that if you have a beam of neutrinos versus a beam of antineutrinos, and in vacuum, they would both be potentially in vacuum, they're identical, and you just get this black curve. But when they go through matter, you expect a little bit of a difference due to this matter effect. And for the normal ordering, it means you get a little bit of an enhancement of the neutrino oscillations and a little bit of a suppression of the antineutrino oscillations. And then this would flip signs for the inverted ordering. And this is, for example, what this effect looks like in the case of T decay with a distance of 295 kilometers. If you were at a longer baseline experiment and we're looking at the neutrinos after a distance of 800 kilometers, for example, this effect becomes larger, right? This splitting between what would happen in vacuum and then in matter effect. So you expect to see some difference between neutrinos and antineutrinos when they go through matter, but this is something that you can calculate, and this isn't a continuous parameter, right? It's the normal ordering, or it's this flipped around the other way. It's the inverted ordering. So it's just an either or situation. There's not a continuous parameter associated with this. This again is something we can calculate. But there's an additional difference between neutrinos and antineutrinos that can come in from that parameter delta in that mixing matrix. We have those e to the I delta terms, and it means that you end up with oscillation terms that scale as minus sine delta for neutrinos and plus sine delta for antineutrinos. And so this means that now if delta is not equal to 0 or pi, this now means that even in vacuum, you'll start to see differences between how antineutrinos oscillate and how neutrinos oscillate. And so even in vacuum, if delta is not 0, then we do expect to see a difference between them. And so I'll try to show an animation of this. This is assuming the normal ordering, and starting with delta equals to negative pi, where there shouldn't be a difference really. And again, we expect a slight difference between neutrinos and antineutrinos just due to the matter effect in this case, if they're traveling a distance of 295 kilometers. But if we start to change the value of delta, as delta becomes large and negative, especially around negative pi over 2, we saw a big increase in the neutrino oscillations and an equivalent suppression of the antineutrino oscillations. And when delta is positive, the opposite thing happens. So I'll replay video again. Negative values of delta, we see more neutrino oscillation. Positive values of delta, like now, we see more antineutrino oscillation. And here, delta is a continuous angle somewhere between minus pi and plus pi. And so there's this fundamental difference between neutrinos and antineutrinos, depending on this parameter delta that we don't know. Right, and that's what a lot of this measurement, this new result from TDK, is about, this parameter delta. So, oops, sorry. For 4 more seconds. So why is this parameter delta important? What does it mean if neutrinos and antineutrinos don't behave in exactly the same way? So there are a couple of fundamental symmetries of the universe that we could think about. If we could ask what happens to the universe under charge conjugation, where we replace all of the particles with antiparticles. That would be a charge conjugation transform. Or we could also have a parity transformation where we invert all of the spatial coordinates. So in this case, the particle's spin would remain the same, but for example, its momentum vector would flip around. And so this parity transformation has the effect of converting a right-handed particle into a left-handed particle, whereas this charge conjugation transformation involves converting a particle into an antiparticle. And so we know that C and P are both violated in weak interactions. But as far as we can tell, CP seems to largely be conserved. It's conserved in strong interactions, and in weak interactions, it mostly seems to be a good symmetry. So CP is the combination of both of these transformations together. So it means turning a left-handed particle into a right-handed antiparticle. So if CP is a good symmetry of the universe, then left-handed neutrinos and right-handed antineutrinos should behave identically, and we should see exactly the same physics. Now, we've known for a while that there is a little bit of CP violation that's seen in the weak interactions of quarks. There's decays of certain neutral mesons that prefer to decay to one charge configuration to another, but it's relatively small. CP violation hasn't been definitively observed, though, with leptons, like electrons or neutrinos. And we really are looking for sources of CP violation in the universe because we live in a matter-dominated universe today, but we presume that in the Big Bang, there were equal amounts of matter and antimatter that were produced. And so there have to be some processes in the standard model that treat particles and antiparticles differently. And again, what we see in the quark sector is pretty small, and it's difficult to explain what we see in the universe today. And so we're really wondering if maybe the key to this is lying in the lepton sector, and this is something we can probe with neutrinos. So with long baseline beams like T decay, the big questions we're trying to answer, there's still big remaining questions about the mass ordering. This angle theta 2,3, is it exactly 45 degrees or not? If it were exactly 45 degrees, again, we kind of have this symmetry, this equal mixing between mu and tau. But we also really want to know about this parameter delta, which again would give differences in neutrino oscillation probabilities for neutrinos versus antineutrinos. And if this is sine of delta is not equal to 0, then it means we have CP violation in the lepton sector. And again, this can be an important clue to how the universe got to be what it is today. So these are the kinds of questions we want to answer with long baseline beams. There are also still there are additional really important questions about the nature of neutrinos and the masses of neutrinos and also potentially looking for different mass splittings or different scales or signs of additional sterile neutrino species that people are trying to answer with a lot of other really important experiments. But this is mostly what we're focusing on at the moment with long baseline beams. Right, and you may wonder, why do we care about these neutrinos at all? Okay, they have tiny masses; they hardly ever interact. Why do we care at all? Again, maybe if we see CP violation in leptons, again, this may be an important clue to how our universe came to be matter-dominated today. Also, as tiny as neutrinos are, with these masses, they're at least 1 million times lighter than an electron, for example. They still could have played an important role in how structures form in the universe, for example. These are simulations of the large-scale structure of the universe if you have massless neutrinos versus fairly heavy neutrinos. And neutrinos tend to have the effect of smoothing out density fluctuations in the universe. So here things are a little bit clumpier, or there are more filaments, whereas these neutrinos, even though they still have very tiny masses, there are enough of them that they can kind of smooth out some of these fluctuations in the large-scale structure of the universe and also in the cosmic microwave background. And so, we want to understand what role do they play in the universe. And also, neutrinos, because they have no electric charge, are also a really useful probe of a lot of astrophysical phenomena. What's going on in supernova or the core of the sun, or other distant energetic phenomena. And that's because, unlike photons, which can get absorbed, or charged particles, which can get deflected by magnetic fields, right? Neutrinos just stream through the universe in a straight line. And it was also still just maybe the question of neutrinos seem to have very different properties than the other particles. And their masses are much smaller than the other particles. And again, is there just something fundamentally different about them, the way they get their masses? Are they somehow a different type of particle in the standard model? So there's still a lot of big questions that we're trying to ask in neutrino physics, but I'm going to switch gears and mostly talk now about, for the remainder of the talk, about the TDK experiment. One of the neutrino projects I'm involved in, and this is a long baseline neutrino experiment in Japan. We produce a beam of neutrinos here in Tokai on the east coast of Japan. The neutrinos travel through the Earth for 295 kilometers to the Super Kamiokande detector. Super Kamiokande has been running since 1996, and we are pointing this beam at it. And in addition to the Super Kamiokande on the other side of Japan, we also have a near detector located on the J-Park site that's about 280 meters away from the target where we produce the neutrino beam. So how do you actually make a beam of neutrinos? I mean, I've said they have no mass and no charge, and yet somehow we can make them with an accelerator. What we do in a neutrino beam is very similar to what happens in the atmosphere when you make atmospheric neutrinos. You start with high energy protons. In the case of TDK, these strike a graphite target, which is roughly the size and shape of a baseball bat, and they produce pions and kaons, which are short-lived particles, and eventually decay to produce neutrinos. In TDK, we use 3 magnetic horns to try to focus these pions and kaons into the desired direction, and then we give them a 96-meter-long decay region where they decay mostly to muon neutrinos. And then we have dirt and sand, and that stops all the charged particles eventually, but the neutrinos keep traveling through the Earth towards our detector that's 295 kilometers away. The beam that you get as a result of this in TDK is about 95% muon neutrinos, a couple percent antineutrinos, and there's a little bit of electron neutrino component in it, but it's mostly a muon neutrino beam, and so we're mostly looking for the disappearance of muon neutrinos and the appearance of electron neutrinos. It's a little bit harder for us to detect tau neutrinos at these energies. We could make a beam that's primarily antineutrinos if we change the direction of the horn current in the magnetic horns so that we focus negatively charged particles instead, and then those will decay to produce antineutrinos instead. So the accelerator facility that we use is the J-Park facility on the east coast of Japan. Really is right on the ocean here, and the protons are accelerated through an accelerator chain up to 30 GeV. We have a very intense proton beam, and but it's very short in duration. So about every 2.5 seconds, we get a 5.2 microsecond wide pulse of 10 of the 14 protons that strike the target, and then the neutrino beam travels off to the west. So TDK has been taking physics data since 2010, and the data that I'm going to be talking about here, the data set I'm going to be talking about is for runs 1 through 9. So this is data that was collected through 2018. There is additional data that was collected last year, and so there will likely be an update in the future. We have 30% more forward horn current data. The first couple of years, T2K operated in forward horn current mode. That means we were producing primarily neutrinos. Starting in 2014, we also began to collect data in reverse horn current mode, which means you have a primarily anti-neutrino beam. This total, the total data set that I'm talking about here is only about 50% of the total data set that T2K hopes to collect. And also our beam power has been going up, and we're now operating around 500 kilowatts. So T2K has, as I mentioned, near and a far detector. What's maybe a little unusual at first, if you haven't seen this before, is that we don't actually point the neutrino beam directly at Super Kamiokande. And that may sound a little bit crazy, because surely we're getting a lower neutrino flux by not pointing our beam and our decay volume right at Super Kamiokande. But if you compare what you see if you were sitting right on the axis compared to what happens if you go a couple degrees off axis, it's true that the overall integrated number of neutrinos that you get goes down. On the other hand, you get a much narrower beam. And since neutrino oscillations are a function of energy, it's nice to have a very nice narrow energy beam for these purposes for T2K. So T2K, again, is about 2.5 degrees off axis. And we have a near detector that sits on the same off axis angle like Super Kamiokande. So when neutrinos pass through our detectors, we don't actually see the neutrinos themselves, but when they interact, which again is still relatively rare, they produce charged particles in the detector that we can look for. And a particularly nice channel to look for are these charged current quasi-elastic interactions, where a neutrino comes in and produces a charged lepton in the detector. And if you can measure the type of lepton, you know what type of neutrino you had. And if you can measure the charge sign of the lepton, whether it was positive or negative, then you know whether you had a neutrino or anti-neutrino that produced that interacted in your detector. At the energies relevant for T2K, there are also a couple of other slightly more complicated reactions that can occur, including resonance production like this, where we can produce a pi plus. We also can have coherent pion production, and also some deep inelastic scattering, where the neutrino is almost interacting off of a cork inside, and we get a number of particles that come out of this. These are all charged current interactions, where you get a charged lepton that comes out. There are also neutral current interactions, or processes that can occur as well. So how do we actually detect these neutrinos? Again, we don't see them themselves, but we see the charged particles that they produce. And we use a bunch of standard particle physics techniques, sometimes multiple techniques in one detector. And one way you can look for the charged particles is the ionization that they produce. And you can then try to collect or drift these electrons and figure out where the charged particles were passing through your detector. Sometimes you can also take advantage of scintillation light, where you have an excited molecule that emits visible light as it returns to its ground state. And T2K's near detector uses a mixture of ionization and scintillation detectors to track the charged particles in it. The far detector, however, uses Cherenkov light. So this is something that occurs when a charged particle goes faster than the speed of light in a particular material, and you get a little cone of light that's produced. And so again, our far detector is primarily a Cherenkov detector. So the near detector has many different components to it. There's something like 10,000 neutrino interactions per day inside the near detector when the beam is on. And at the heart of the near detector, we have these fine-grained scintillator trackers that are plastic scintillator bars. They're bars that are 1 centimeter by 1 centimeter, and we have layers of these with the bars going in alternating directions. These are sandwiched between, in a club sandwich configuration, I guess, between 3 time projection chambers, where we can make really precise measurements of the tracks. Upstream of all this, there's a pi-0 detector, which is essentially a kind of electromagnetic calorimeter designed to really look for the production of pi-0 events. I should say that one of the FGDs and part of the pod also have some water in them as well, which is important. Most of the NIR detector is plastic, but our FAR detector is made out of water. And so it's nice to also have some water samples in the NIR detector so that you're looking at neutrino interactions on the same molecule. There's an electromagnetic calorimeter and also muon range detectors that surround the whole detector, and it sits inside a magnet so that in the NIR detector we can tell what the charge was of the particle, so we can tell if it was a neutrino or an antineutrino that interacted in the detector. So this is an example of an event display from the NIR detector. We have simulator bar hits here in the pi-0, so the neutrinos come in from the left. We had an interaction roughly here. We can see these simulator hits, but also these nice curving tracks in the TPC. The FAR detector is quite a different detector technology. The FAR detector, because the flux is so much lower, has to be very large, right? In Super Kamiokande is a giant tank of ultra pure water. It has 50 kilotons of water with 11,000 phototubes. You can see there are 3 people here on a little boat near some of these phototubes. There are 11,000 of these phototubes that look inside, and there's also a veto layer outside that can reject out events coming in from outside. And even as big as this detector is, we see maybe a handful of events per day when the beam is on. Events in Super Kamiokande, it's a Cherenkov detector, and so again, we're looking for these rings of light. Muons tend to produce nice crisp rings in the detector like this. Electrons tend to produce fuzzier rings like this in the detector. They scatter a lot more. And so you can use particle identification techniques to try to distinguish between these kind of rings. And we can look for muon-like rings and electron-like rings to tell what kind of neutrino interacted in Super Kamiokande. So the oscillation analysis ends up being fairly complicated. Our detectors are quite different from each other, so we can't just count the event rate in the NIR detector and compare that to the event rate in the FAR detector. And so I'll try to walk you through some of the key steps of putting all this together to fit for neutrino oscillations. Right, and so one of the important things to understand is the flux of neutrino flux in the experiment. So neutrino production processes are pretty complicated. When these protons interact in the target, there are multiple charged particles produced, and these particles can re-interact, and also in the horns, etc. And so it's difficult to calculate this, and when TDK started, there were something like 20 to 25% uncertainties on what the flux is that comes out of this beamline. We have a lot of external data from, for example, the NA61 experiment at CERN, where we actually measure the particles that are produced when the protons interact in the target. And this has been able to reduce the flux uncertainties in TDK by roughly a factor of 4 to 5. And we're also trying to do similar measurements for other experiments, like, for example, upcoming DUNE experiment. And so, again, what we're using currently in TDK, we have a lot of data with 31 GeV protons striking a thin carbon target made out of the same kind of carbon as the TDK target. And we measure the charged and neutral particles that come off of this and use that. So on the right here, this is an example of the yields of pi plus, for example, and then you can use this to understand what neutrino flux you get when these pions decay. We've also taken data in NA61 with a full-scale TDK target, and there are measurements published with this long target data, and in the future, TDK will start using this replica target data to predict the flux. So we use this to understand the flux, and we can use that to relate things between the NIR and the FAR detector. Then we also have the neutrinos interact inside the detector, and we have a model for what happens when the neutrino interacts in the detector. Neutrino interactions in this energy are actually relatively complicated. They're not just interacting with a single quark, and they're not just interacting with a single free neutron or something like that. So first you have to take into account the fact that you have nuclei and some sort of nuclear model for that. It also turns out there's evidence that the neutrinos may not just be interacting with a single proton or neutron, but potentially can be interacting with correlated pairs of nucleons. And then even once you have this interaction inside the nucleus, you could potentially produce a pion, but it has to escape from the nucleus, and there are additional processes that can occur, such as the pion being absorbed. So it can be difficult to model all of these, and again, having a really precise mirror detector can really help you constrain this. And a lot of these issues are going to continue to persist in the future, on targets like argon for things like the Dune experiment. So we have a complicated interaction model, but we can use the mirror detector in combination with our cross-section model and flux prediction to try to reduce these uncertainties and extrapolate to what we expect to see on the other side of Japan in Super Kamiokande. So in the mirror detector, there are a bunch of different samples. In neutrino mode, it's based on all of these are charge current channels that require a muon like track, and then they're distinguished by the number of other tracks that are appear in the event. In anti-neutrino mode, it's again just based on the total number of tracks. And then all of these samples are repeated. There are two fine-grained detectors, one of which is entirely hydrocarbon and the other of which has some water in it. And so we use both of these samples to try to really constrain both the flux and interaction model. So for example, there are these 14 different samples. These are examples of two of these samples that are binned in the lepton kinematics. The black shows the data, and the various colored lines show, after we do a fit, the agreement between the data and Monte Carlo for which helps us to sort of tune our model for how neutrinos interact and what the neutrino flux is in the beam. So we can combine all of this and try to predict what we'd expect to see at Super Kamiokande. And so this is the predicted number of events that you'd expect to see at Super Kamiokande. The orange is what we'd expect to see with no constraints from the near detector, just external measurements. The blue is what we get when we now combine all this external input with what we see in the near detector. And so the near detector overall reduces the uncertainties by something like a factor of 2 to 4. So it can really help to reduce a lot of these uncertainties. So we then know what we expect to see at Super Kamiokande if there aren't any oscillations, and then we can try to actually look at what we see in the data and compare what we observe to what we expect, and try to associate that with neutrino oscillations. So for muon neutrinos, again, it's primarily a muon neutrino beam, and this is an old plot just because it actually shows what we would expect with no oscillations. So this is what we get from the near detector and the Monte Carlo, and the black is what we actually see. The red is the fit that we get. If you see the ratio of what we actually observe to what we predict, you see this really nice dip, again, characteristic of what we expect for neutrino oscillations. And again, at certain energies here, you have something like a 90-95% almost complete transformation of this muon neutrino beam into some other flavor. So again, we don't intend to show this anymore because the oscillation signal is just so large for muon neutrino disappearance. So we see very significant muon neutrino disappearance, and we also see the appearance of electron neutrinos on the other side of Japan. Again, this is a slightly earlier result where without any oscillations, we expect a background of about 5 events, and instead we saw 28 events. And again, you can fit that pretty well to oscillations. So we know we have significant muon neutrino turning into electron neutrino as they go through Japan. And the thing that we're really focusing on the last couple of years now is trying to compare that for a neutrino beam to an anti-neutrino beam. And, sorry, I actually can't see the time. Can someone tell me maybe how I'm doing on time?
Yes, yeah, it's 4:45, so we are 45 minutes into our seminar. Okay. And if you have any questions in the audience, if there is any questions, please send them to me via the chat box directly. The meeting chat, unfortunately, does not appear to be functional at this point, so you may not be able to find it directly.
Okay. So again, we see this significant flavor transformation, and what we're really interested in now is neutrino mode versus anti-neutrino mode. And in neutrino mode, we have 2 electron samples and 1 muon sample, and these are 2 samples in anti-neutrino mode. And if this delta CP parameter, that delta is 0, for example, this is what we would expect to see compared to what we actually see. And if we just compare the raw event numbers, what we actually see, we see a lot more electron-neutrino events appear in neutrino mode, whereas in anti-neutrino mode, we see fewer electron neutrinos than compared to what we would expect to see. And so it seems that we definitely see oscillations in both neutrino mode and anti-neutrino mode, but we seem to see a higher rate of oscillations in neutrino mode and less in anti-neutrino mode compared to what we would expect if this delta CP parameter were equal to 0. And so when we actually do this fit, we do more than just count the number of events. We also fit the energy spectra, or look at these oscillations as a function of energy. And so we can try to do a fit and ask what are the best values of the oscillation parameters. And so these are our results that came out last month in Nature. If you just look at T2K alone and plot the 68% confidence level, there's this mixing angle theta 1,3 that tends to dominate this muon to electron oscillation. And there's also this value, again, delta CP. And this is just at the 68% confidence level. And if we use a constraint from reactor neutrino experiments, which can constrain this theta 1,3 parameter better, and we combine that with the T2K data, then we get something that looks more like this darker blue line here at the 68% level. And so delta CP equals 0 or pi is excluded at the more than 95% confidence level when you use the T2K data, and very far away from it being 0. And if this is what in this Nature paper, for the first time, we drew 3 sigma contours. And so this is what you get if you draw the same thing with 99.7% confidence levels. This depends on whether you're assuming the normal ordering or the inverted ordering. But if we look in the normal ordering, we can see that delta CP equals 0 is actually is excluded, actually in either hierarchy. Delta CP equals plus or minus pi is excluded in the inverted ordering and is heavily disfavored, but there is still a little bit of possible at the 99.7% level. There's a little bit of allowed space there. And so this means at least delta CP equals 0 is now excluded at the 3 sigma level. And again, the other CP conserving value is strongly disfavored. Our best fit actually ends up being pretty close to something like minus pi over 2. And so this means that potentially there is very large CP violation. Minus pi over 2 would give us maximal CP violation. And so, right, so at the roughly 3 sigma level, again, we see pretty strong evidence that delta doesn't seem to be consistent with being 0. I'll also note that we don't, at the 68% level, we actually don't have any phase space for the inverted ordering. So this is also strongly disfavored. So we can't claim, again, this is only at the 3 sigma level, but we definitely see pretty strong hints that it looks like this CP violating parameter for leptons may actually be quite large. And there may really be very significant, almost as large as we could imagine, differences in the way that neutrinos oscillate compared to antineutrinos. So what's next for T2K? T2K has been proved for a factor of 2 more protons on target, and there are intensity upgrades to the beam. There's a T2K2 proposal that proposes to extend this through the end of 2026 and to get another factor of 3 more data there. And again, we should be able to reach 3 sigma exclusion. And again, frankly, we're very close to 3 sigma exclusion right now with the data that we have in hand for the CP conserving value. There's also an upgrade in process going on to T2K's near detector. There's a reconfiguration of the near detector, so the TBCs in the FGD remain, but there's a super FGD that is being constructed here. The super FGD is made, rather than long bars, it's made of little cubes of scintillators, so you get much better 3D tracking of the events, and it's also there are these horizontal TPCs that provide better high-angle coverage. So one of the issues with the current configuration of the TDK detector is that we have very good acceptance for forward-going events, and then we're not so efficient at detecting things that come off at big angles. And so this is going to help improve that and give us better sort of 4-pi coverage to these neutrino interactions. And so there are a number of groups heavily involved in starting to assemble parts of this. Looking a little bit more to future long baseline experiments, what the future holds for TDK, there is another project called HyperCameo Conde, which would use the same beamline in TDK from JParc, but there would be a new, larger FAR detector that would be built, and potentially additional, there's some possibility for maybe a detector in Korea as well to compare these oscillations at different baselines. And there's also a similar effort going on in the US, the DUNE project, which would have a new beamline from Fermilab to South Dakota with a longer baseline of 1,300 kilometers. So I'll briefly mention, as you hopefully know, there are a number of people at Arlington who are involved in the DUNE project, but DUNE will have a new high-intensity beam, and the proposal is to have 4 roughly 10 kiloton detector modules. Of the exact details of some of those modules is still open for some discussion, but these modules will be, at least the first modules that are planned will be a mixture of single phase and dual phase liquid argon TPCs. So the liquid argon gives you really nice, precise tracking measurement and also a nice dense material for the neutrinos to interact with. There also will be a near detector that has several different components, including a liquid argon component to the near detector, and again, hopefully a gaseous argon TPC following that. For example, in DUNE, again, DUNE can try to look for nu mu turning to nu e, and the same thing for antineutrinos. This is what you'd expect to see in DUNE for the normal ordering, for example. And so you'd see significant differences between neutrino mode and antineutrino mode. And also DUNE, with its longer baseline, should be able to really very definitively resolve this question about the mass ordering. So DUNE should be able to resolve this mass ordering question at the better than 5 sigma level. And for about 80% of the possible range of delta, again, from minus pi to pi, DUNE should be able to resolve that at the 3 sigma level for more than 80% of the possible values. So if delta CP really is at the value that TDK currently likes of negative pi over 2, again, this would provide pretty significant signal in DUNE and other future long baseline experiments as well. So in conclusion, there's very strong evidence for neutrino flavor change, and current long baseline measurements are making increasingly precise measurements of these mixing angles and these delta M squareds. Again, we see a more than 2 sigma difference, really close to 3 sigma difference in oscillations between neutrinos and antineutrinos that can only be explained by there being some non-zero value for that delta CP parameter. And so there's still a lot of unanswered questions that we're trying to address with beams. Like, again, we don't know which neutrino is the lightest. And again, we'd like to really more definitively understand whether or not neutrinos and antineutrinos have the same mixing properties. And again, if sign delta is not equal to 0, that's a really pretty fundamental discovery of CP violation in the lepton sector. And future experiments like DUNE will continue to answer these questions over the next decade and beyond. And so with that, thank you very much.
Clap, 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 clap.
All right, thank you very much. Alysia, for this wonderful talk. I'm sure everybody is doing a virtual clap right now. Unfortunately, we have so many questions, but unfortunately, this meeting chat did not work properly as it should work. And I'm even trying, give me a second. I'm going to read them one by one to hopefully answer them all. So one student asks, is it only the electrons in a material that affect neutrino oscillations at T2K, or do nuclei and nucleons also have matter effects in the oscillations?
Oh, in the matter effects, it's just the for that particular scattering mode, it's just the presence of the leptons, because that charged current channel, you need to have a lepton, and so it's the electron neutrinos or antineutrinos that have a charged current channel because of the electron. So it's the presence of the electrons that create that matter effect.
Okay, thank you. And then the next question is from another student. Do you see evidence that the nuclear effects are different on hydrocarbon or water?
There are measurements now in TDK of both the cross sections on water and oxygen. I don't think at the moment we yet have a lot of detailed measurements about the. I don't have a good summary plot with the various cross section measurements. Certainly, the cross sections are a little bit different from each other, but details of things like the momentum balance and things like that are still being looked at heavily in the near detector. I should also say that there is an on-axis near detector, which I actually didn't say much about earlier. Sorry, which sees neutrinos at a slightly different energy, and there's some water detectors there as well. And so we're increasingly trying to combine a lot of the different water detectors to try to make these measurements over a broader energy range.
I see. And the continuation of that question is, how much impact does that difference have on the oscillation results?
I can't remember. It used to be that a lot of the remaining cross-section uncertainties when you got to super K actually did involve extrapolation between the difference between carbon to oxygen. Again, we have better constraints on the oxygen now, but it's still true that I don't know if I have a nice plot of this. So these show, for example, the systematic errors. And so if you use the combined beam and cross-section constraint on these various samples at super K, they really are at kind of the 3 to 4% level. And then when you put in the additional uncertainties at super K, and this includes some additional cross-section uncertainties and final state interactions and things like that, then you kind of doubles the error there. But again, that's not just, some of this is cross-section and some of it is also detector systematics. So I think it used to be one of the biggest remaining cross-section uncertainties was the difference between carbon and oxygen. But at the moment, near detector constraints and super K constraints for a lot of these samples are kind of at the same level.
Thank you. And we have another question from another student. In our journal club, we noticed that the nu bar differences seem perhaps even larger than the expected, the maximal CP hypothesis. Is the nu bar asymmetry consistent with expectations for dCP equals half pi, or is it even larger?
So the largest effect you can have is really at delta CP is pi over plus or minus pi over 2. It is true that this particular channel, this new, I think this is what the question was asking about. I didn't quite hear. Sorry, maybe you should repeat the beginning.
Yes, sure. Which part of it? So I repeat the last part of the question. Is the nu bar asymmetry consistent with expectations for dCP equals half pi, or is it even larger?
Yeah, so the biggest asymmetry you can get is at half pi. And so the fact that we observe 15 when the largest amount we would sort of predict is 7, it is bigger than you would expect just from delta CP not being equal to 0. It's consistent with it in this mode where we have better statistics and actually much smaller systematic. So in this NUI channel, it actually agrees pretty well. It is true in this sample where we allow for one pion that can decay to an electron. The excess we see is actually bigger than we would have expected to see. On the other hand, this is also the channel that has by far the largest systematic and statistical errors on it. So it's not completely unexpected just from statistical fluctuations, but it is true, yes. There is the fact that we see a lot more, but even in this channel that is better has much better statistics, it's still pretty consistent with pi over 2.
Thank you. And another question from another student we have, is the CP violation angle flavor dependent?
Is it flavor dependent? There is only one CP angle that occurs in the oscillation matrix for 3x3 oscillations. So at least for 3x3 oscillations, there's just a single delta CP that shows up in all of this.
Thank you. And then we have one last question from one of our postdocs. Are there any physical implications if delta CP is negative versus positive? Like
if delta CP is negative versus positive? Not that I can think of. I mean, in the case of neutrino oscillations, it's because things are proportional to negative sign delta, that if delta is negative, it means you get more neutrino oscillations and less anti-neutrino oscillations. So maybe in some complicated leptogenesis scenario, it being positive versus negative might mean something, but I think at the moment, I think at the moment the fact that it's not 0 is really what we're interested in trying to see. And I'm not, so again, it does affect whether you get an enhancement of neutrinos versus antineutrinos, it being positive versus negative, but I don't think we expect one way or the other that it should be positive or negative.
Thank you. And I believe your response already addressed this fully, but I just want to repeat the full question. The rest of the question is like, do the leptogenesis models require a negative or positive delta CP?
Again, I'm not sure, but at the end of the day, maybe it does have, I don't know, I'm not sure. It is true that we get more positrons, I guess. I'm not sure.
Right, thank you. And I believe these are all of the questions that I have received from the students and postdocs and everyone else. I think with that, we're going to conclude our last colloquium of this eventful semester. And thank you very much again for your time, Alysia. It was a wonderful time.
Great, thank you. And I hope we all have less eventful semesters.
Thank you. Thank you.